Good evening, everyone. Welcome to the August meeting of the Ottawa Centre. Welcome to those joining us online or who have downloaded this to watch later. Thank you very much for taking the time to come today. I noticed we got a good crowd today. I know the summer months are usually a bit thinner, but I believe Starfest is also on, so so I'm not surprised that it's a bit less than we normally have. Thank you very much for coming down, for those of you who have come down, and for those of you who are joining us online. So we'll get right into it. Many of you will have seen the email. And we have a very special guest today, so the program will be a little bit different than usual. But to accommodate our guest, because he has a nice, interesting, long talk, we've kind of shuffled the schedule around to give him the most time so that he can present his topic. So we'll just get right into it then. Once again, the lectern isn't working, so so to the presenters, please make sure you angle your voice into the microphones when you turn around. But this is the program for today. My usual introduction, then I'll briefly mention Mr. Weldon Hannaford. Then we'll have Dave Chisholm and his Ottawa Skies for August. We'll have a mention of the public star parties, the observations, then there'll be the break, and then we'll have Mr. Paul Schultz, who's our very special guest today, with his talk on fast radio bursts. Then we have announcements and door prizes. So these are our new members who have joined in the last month, and special mention to Mr. Jose Campos, who I believe joined just this afternoon. So, and of course, Linda Meyer has also joined the organization. So I hope you find the organization as enjoyable and as stimulating as I have over the years. Welcome. So we've had 42 new members in 2016 so far, including at least 2 families. And so this brings us up to past the 50 mark. Members in the news. This was the launch of a telescope lending service at the Nepean Library. This is actually now held. There's a telescope that's now being held for loan at the Centrepoint branch. This is basically almost exactly the same way our telescope lending library works, and now you can do it at a public library. And I believe that's Mike Mogadam right there. And this telescope was donated by one of our members, Mr. Mark Narwa. And so I believe that's the scope. And this was in the Canadian newspaper. And you can now go to the Centrepoint Library and rent it out. I'm not sure if it's available for interlibrary loan, but
it's not, Roman.
Oh, it is not. Okay, it is not available for interlibrary loan. So if you were interested in getting the telescope, you would have to go to Centrepoint and probably check with them to make sure that it's still available. Last month, we paid tribute to 2 members who had recently passed away. We dedicated the meeting to the memory of Rolf Meyer, and we were also speaking of Mr. Weldon Hannaford. Now, there was a lot of emphasis put on Rolf, and I hope that no one who knew Mr. Hannaford or a member of his family felt that we were trying to diminish or slight his long contribution to the RESC, notably in helping construct SmartScope. It was strictly a matter of timing. Rolf unfortunately passed away. It was towards the end of June, and Mr. Hannaford passed away at the beginning of July, and I believe it was only the day of or the day before the meeting that we actually found out. So if anyone was wondering or felt slighted, we apologize. It was strictly a matter of timing. Mr. Weldon Hannaford, I never knew personally, but he seems to have had a big impact on a lot of the members of the center. And as I mentioned, one of his major contributions was assisting in the construction of SmartScope. We have oh yes, that's a photo of him in the construction. We have a clip of a talk that he gave. For those of you who were here last month, we played a clip of Rolf Meyer giving a talk, and this is a clip of Mr. Hannaford giving a talk. It's on cosmic rays.
Ready? Go. In the year 1912, an Austrian scientist named Victor Hess went up in a balloon with 3 ion detector instruments on board. His purpose was to prove that the Earth was a source of ions seeping up out of the ground, and of course they should diminish as he rose higher and higher. But instead, he discovered that the ionization rate was increasing as he went up. And when he got to the top of his climb, 17,000 feet, the rate of ionization was 4 times greater than he had measured back on the ground. And so Victor Hess had just discovered cosmic rays, and for that discovery, he received a Nobel Prize. Unfortunately, the newly discovered phenomena acquired the name cosmic rays before its real nature was discovered, and the name cosmic rays stuck. However, they're not rays, not like X-rays or rays of sunshine. Cosmic ray is a stream of particles, mostly protons, but wait till I get this fixed here. Also nuclei of hydrogen, helium, including neutrons, of course. Very rarely even some heavier nuclei. The task of collecting a useful quantity of extremely rare, ultra-high energy cosmic ray particles within a workable time requires a very, very large array. There are, or there has been, as many as 4 such arrays in the world. The Pierre Auger array in Argentina is by far the largest and best equipped. A consortium of 330 scientists and 32 organizations has recently built and put into operation in January 2004 the Cosmic Ray Observatory, named after Pierre Auger, a pioneer in the study of cosmic rays. Okay. The information from 2 or more telescopes will reveal the azimuth and slope of the incoming particles, and the intensity of fluorescence will provide a measure of the energy, as well as will the Cherenkov radiation in the tanks. Each of these little asterisks is one of the AGNs, or black holes, in the catalog. And of course the thing to see is how they coincide with these rings that are the calculated positions. Well, there's 1, 2, 3, 4 calculated positions. This one here has 4 or 5 AGNs right around the perimeter. This one has 1 AGN where the 2 rings overlap. There's 3 coincidences here. Isn't that typical of astronomical research? Every mystery that's solved just reveals another mystery. There's just one other item I should mention, and it involves the Big Bang and the residual cosmic microwave background. 3 physicists named Grayson, Zatspin, and Kuzman theorized that ultra-high energy cosmic rays would interact with the weak 2.7 degree Kelvin cosmic microwave background and they'd lose their significant energy if they had to travel beyond 600 million light years. And this is known as the GZK effect. GZK is the initials of the three authors of the theory. The science article says that the data on the highest energy cosmic rays confirms this GZK theory. But the article does an obscure job of explaining how. I think their observations show a rather abrupt cutoff in energy among the showers that don't coincide with anything. And that, folks, is the end.
Thank you, Willie.
Oh.
Well done, Hannaford. We wish you clear skies. So moving on, we have Dave Chisholm and the skies for August.
Okay, good evening. So let's just we'll start with the moon phases for August, and the full moon is on August the 18th. Our big event this month, obviously, is the Perseid meteor shower, best viewed overnight, August 11th to the 12th, best after midnight when the moon sets. Probably about 1 a.m. would be a good time to see the Perseids. The Perseids are a result of the comet Swift-Tuttle and the debris that it left behind. And if you are not around on August 11th and 12th, they're around till August 24th, but they really peak on that time frame. Planet Mercury is visible in the evening sky with its greatest eastern elongation on August the 16th at sunset. Venus is visible in the evening sky, and there's going to be a conjunction of Venus and Jupiter on August the 27th, 0.06 degrees apart. It's pretty close together. And Mars will be visible all month. Jupiter's setting pretty early these days, but the skies are getting darker earlier. So Jupiter's sort of visible all month, but in particular on August 27th, when the conjunction of Venus takes place, is probably the best time to try to find it. Saturn is visible all month. Uranus and Neptune, again visible all month. International Space Station, best viewing date is August the 10th, where it rises to 88 degrees, so it's almost directly overhead. The next slide here shows you where it is in the sky. And I get these predictions for the ISS from heavensabove.com. Great website for that. And I leave you with this little cartoon at the end. That's where crop circles came from. Okay, we're going to move on. I've got another quick presentation after this. And one of the things I like doing in my spare time is looking at cool projects that come up on a funding site called Kickstarter. And one that came up about a month ago was the Lola Observatory. And what they are doing is that they are restoring the telescope that Clyde Tombaugh used to discover Pluto. And so they're doing some fundraising for that. And I'm going to show you a short video, and then I'll just explain to you how Kickstarter works.
I'm sitting here at the very telescope where Pluto was discovered by Clyde Tombaugh back in 1930. This is a really historic astronomical telescope because it not only resulted in the discovery of Pluto, but it led to our current understanding of the solar system. It led to the discovery of what we call the third zone, the true outer solar system where Pluto orbits. And it led to the New Horizons mission that flew all the way across the solar system to explore Pluto. And I'm asking for your help to restore this telescope to its original beauty and grandeur as an inspiration to people for decades to come who can come and stand here in the very dome where Pluto was discovered, where Clyde Tombaugh did his historic work, and know that you were a part of inspiring a new generation to be excited about science and astronomy and spaceflight and about all of our future. Help us restore this telescope and be a part of something a little larger than life. Thank you very much.
Okay, so the way they are fundraising is on this website called Kickstarter, and the URL is at the bottom of the screen there. That's quite a long URL. If you go to www.kickstarter.com, click on the search button and search for Pluto. That's the fastest way rather than to type all of that in. The way it works is a pledge system. At different levels of pledges, there's different rewards. At the basic level, you get a postcard, all the way up to the $1,500 level, where you get to sleep in the apartment that Clyde Tombaugh slept in, plus all the other benefits of the system. And there's some really cool things in there. Take a look at it. It is a pledge system. They do not get the money unless their goal is met, but they're doing pretty well. Right now, they've raised about $21,000 of the $22,765 goal. So they're like 93% of the way. And I'm one of the supporters, and if you're interested in this, I'd encourage you to go to Kickstarter.com. It's fairly straightforward on how you do the pledging. Thank you.
Thank you. Thanks for that, Dave. That telescope, it's in Flagstaff, Arizona, right?
That's correct.
Okay. Will you be sleeping in the...
No, I did not go to that level.
You don't go to that level? No.
I didn't get the clearance to go to that level.
Okay.
I'll get some nice pictures.
Oh, good. Actually, that would be very, very nice, though. All right. So we have... We have pictures from the previous from the last Star Party, which was a great success. And I'll just mention that it happened to be the first Star Party that I went to. So we had there's Chris. So we had a lot of people show up. We had. I'm no good at estimating crowds, but I'd say there was about 7 million people there. Actually. Mike, I noticed you came in. What was your estimate?
Close to 300.
Close to 300. Okay. So again, at the where it always is at the Carp Library parking lot, which is right beside the Diefenbunker. Pretty good skies. And as I said, a really good crowd showed up, and there was some amazing viewing that happened. We saw the International Space Station fly overhead. We saw the iridium flare, that's exactly what I was thinking of. Iridium flare. Then we saw, Chris said that he saw all the planets, he was able to see all the planets before the sunset. I still maintain some of those were airplanes, but Chris has the telescope. And of course, Attila Danko brought his monster scope, which was incredible, just incredible. But thank you to all those who volunteered and to all those who came out. It was a really, really great event. And of course, we'll be having one later on in August, which will be and I'll be making an announcement about that later on in the meeting. But now we'll have the observers come down and just give their observation reports. We have quite a few images. So if we could have Gord Webster and Taras Rabarski come down, please. And but our first images are from NASA. Unfortunately, NASA couldn't make it. Apparently, they have something better to do.
Is that a spokesman?
Sorry?
They didn't send a spokesperson?
So there's something called Juno, apparently, which is like a. I thought it was a movie, but apparently it's something.
I can do it because I'm the one who suggested it.
That's okay. It's the first. Yes, this is submitted by Eric, and what it is, it's the Galilean moons, basically, orbiting Jupiter as seen from the Juno spacecraft. Now, Eric, you might actually be able to answer this, or someone. Is the Juno spacecraft in some sort of synchronous orbit to be able to capture that, or did they
This is actually on the way to Jupiter that it captured this. And what is remarkable about this movie is that it's actually the first time we've actually filmed moons orbiting a planet. That in all these years, we have never been able to do this till now. So that is a unique feature of this, is it's the first time that we've actually captured moons orbiting around a planet. We take for granted that we had films, and yet this is the very first one. It's the very first time.
You know, it's interesting because, I mean, this also helps I mean, for those of a scientific bent, it really helps you calculate, gravity and things like that, because if you can measure the angles, measure the distance, and if you have a few other parameters, you can begin to calculate.
We can go back to that animation again. The other thing is it shows us the 4 moons, and if you're wondering which one is which, most of us do, but Io would be the closest one to Jupiter, followed by Europa, and then Ganymede, which is the largest moon in the solar system, followed by Callisto. So if you're ever observing and you're wondering which moons it is, if you can figure out the order by their distance, that's the order.
It's very interesting. I didn't. Yeah, you never would have thought that we hadn't captured moons orbiting until now. But hey, there you go. All right. So Gordon, take it away.
Well, we recently went on vacation, and unfortunately, while the car was being packed, I had a prior commitment, so I didn't get to say what went in the car, and as a result, my telescope didn't make it. And we were in some fairly dark skies. However, well, there are members of the family who were pushing for the telescope to be included, other than me, and I'm sure you can guess who it was. But the camera did make it, so I thought I'd play with the camera a little bit. And here we are with our tent set up, and you can see the moon coming up through the trees there. And this was a 10-second exposure. I set the camera up on the picnic table, used the remote release. Next, please. I also thought I'd try shooting the sky. Laid the camera on its back. It wasn't quite right, so I had to put a book under it to get it clearing the trees. And you can see Cygnus over in the far. There we go. Thank you, Chris.
Seen in the sky.
And that's a 30-second exposure with the camera just propped with a book under its back to line it up and using the remote release. And then we were at Peggy's Cove, and I happened to spot one of Julia's favorite objects, and I thought maybe she could capture it for us. So we tried this, and Andrew was trying to help. It's a little faint, but I think you can see it there. That's it. Thank you.
Hi, I want to share some pictures, mostly planetary and a bit of the skies. This one, it's image of Uranus. It was taken a few days ago from a fellow observatory. It's quite a zoom. I used 5mm eyepiece, so it gave me with 2000mm focal length of mirror about 400 times magnification. It's not fair to do that, of course, because the limit is about, like, in the best case scenario, 300, so it's a bit downsized, but I actually have to admit that last few, maybe months, if not weeks, I think we had pretty good seeing, so there is a few more pictures which turned out pretty well, and I managed to get some more details from planetary images. Well, being the second furthest planet from the edges of our solar system, we can't really see much details on this one, so I'll just skip on this. But Saturn, however, turned out pretty well. I had another picture like that taken a few weeks before this was taken. And I mentioned that this actually is pretty good resolution, which allowed me to see the Cassini division all around the two rings, so you can clearly see them, even a little bit of planet between them right there. And Titan moon, there is a website where you can enter the exact location and time, and it will tell you where the Jupiter and Saturn moons are located with relation to each other.
Can you point to Titan again, please?
Right there. Same story with Jupiter, which, as Dave mentioned, it's right now getting set much earlier, so it's very low above the horizon, so you cannot get much the details despite even good seeing. So that's why this picture doesn't really have much details, but instead, I think I managed to capture Io, and there was Europa somewhere here, but even when you boost the gamma for the picture on the computer, Europa is pretty dim, so it's not surprising it doesn't show in this picture well. And that's the pretty exciting part about Mars. I was keeping my eye on it since February actually, but the good pictures turned out to be only from March, where it was pretty close to the Earth, and it was moving towards the closest encounter with Earth, which was on May the 30th. You can see how much the size changed within the span of those days. Unfortunately, in April, I didn't have chance to take a snapshot of Mars, but at the opposition and then at the closest approach to Earth, they're about the same size. You can see pretty clearly some details. And then later on, as time passed, it would go further from the Earth and the size would change. And just, I took this image, tried to zoom it to as much as I can size to show some details about Mars, which is, as you know, it's 25-degree axial tilt, which makes it almost exactly the same as the Earth has. So it has exactly the same 4 seasons as we do. And in many other situations, parameters, it's also very similar to Earth. Like duration of the day is about slightly more than 25 hours, if I'm not mistaken. The year lasts almost twice as long, though, 1.9 trillion years. The mass is much lower, though, 0.1 of Earth masses. However, all that mass is still giving 38% of the gravity. So despite much smaller mass, the gravity is maybe slightly less than half of what we experience on Earth. And you know, lots of other interesting facts about it. So I think I won't be really getting into much of the details.
Eric, what scope did you use on those Mars pictures?
The same, which is the Schmidt-Cass with the same 8-inch mirror, 2030-something millimeter focal length, and the same 5-millimeter lens. But that lens, it's kind of really good for photography. It gives you a bit wider field of view, and it gives you a plane instead of spherical projection on CCD, on the camera sensor. And also, this was not actually a single picture. Most of them are up to 10 minutes videos. And 2 different applications were used to process them. First was Registax, which automatically can select best frames for you, then stack them, and then apply wavelength filters to extract the details. The other does exactly the same, but it's a different application used for Mac called Linkios. So when I have those 2 pictures, and then I mix them again to get even more, because usually when you mix like with some percentage of transparency, you get a little bit more details compared to what each separate picture would have. Yeah, you know this object, I guess, well as well. This is a Galaxy NGC 891. It's pretty dim, but it's still one of the best seeing, what you can see in amateur telescope. The interesting part about it is that it's almost the same size, diameter, and appearance as our Milky Way, and it's facing us edge on. So you can see exactly the same dust which we have across the center of our Milky Way. It's concentrated here along those, as I've heard many people compare the galaxies like this as 2 plates put on top of each other, which exactly what this looks like. And the other interesting part is that this is actually a cluster of galaxies. There is a few more of them. There is one also edge-on galaxy right here. I spotted a few. There is one right there and a few others, but they might be too dim to see. So essentially that region is very interesting. There is one like a pinwheel-like galaxy somewhere there, but again, it's too dim. If I expose it for longer, then it may have come up better. You know this object well as well. This is Veil Nebula. It's a little bit different from regular pictures because I used a camera with a modified sensor, so it's more sensitive to hydrogen alpha. And apparently this object has a lots of it. What's interesting is that there is also oxygen part of it, maybe some reflection also, which adds to the bluish greenish color. But what's interesting is that, you know, if we were to see that with our own eyes, even through the filters, we would see just very dim patches of white light. So never actually saw that in color, and whichever rendition comes out of the picture is the interpretation of what you want to show. So in this case, I decided to just simply add lots of that hydrogen alpha to this picture and show how it beautifully glows along. It's actually much larger than this. This is one of the perhaps largest nebulae. It consists of two parts, so this is only one part. It looks like two braces. This is one brace. There is another one somewhere there, and moreover, this brace still goes like this. There is part missing here. I used to think of this as a dragon, this one eye, another eye, nostril, and the mane goes this way, and it's flying in the sky. This is the very same Milky Way. Again, you can clearly see the dust lines here. In the center, North American Nebula, and Deneb star is right. I think this one would be Deneb. So obviously, you know, this is in the constellation of Cygnus, which lies practically on that part of Milky Way, flying through it, or along it, rather. There is also Crescent Nebula right there, Vega, and if I'm not mistaken, the Sadr star right there in the center of Crescent Nebula. So the two major nebula like that are concentrated and practically close to the bulge of, well, not too close, but still in a very bright part of Milky Way. So this picture was taken with all total of 8 minutes exposure. So it added lots of the details and colors, and again with the modified camera we're able to see the hydrogen alpha, how it glows. But I also discovered today, you might have read it in the news, that there is a confirmation that this strange star called KIC 8462-852, which was known for this unusual and irregular and non-explained bursts, or rather a fluctuation in brightness or luminosity. It was confirmed that this actually happens, and we don't have explanations right now why the fluctuation happens. There is like big object which is an obstacle between us, and that star. I think I hit something. Oh, there we go. So that star is actually right there, if I'm not mistaken, somewhere here, according to my checks. There is no, again, explanation. Maybe we are in for another discovery. We would know practically, hopefully within shortest period of time or our lifetime, what is that big object which is an obstacle between us and the whole star. But so far it's just a mystery. Thank you.
Thank you, Gordon and Taras. Okay, so we'll be taking the break now, and we'll be taking a 15-minute break. So if you want to get up, stretch your legs, if someone could come down here and help me with the tickets, then that would be greatly appreciated. Other than that, like I said, 15 minutes, and then we'll be back, and then we'll have Mr. Paul Schultz giving his talk. Okay, so we'll move on to the next talk, and I suppose in keeping with the tradition that, the recent tradition, if that's not a contradiction in terms, that Mike Mogadam started, we're going to have one speaker who has a big talk, and he's come all the way from Montreal today, so I hope you'll make him feel welcome. This is Mr. Paul Schultz. He's a PhD candidate at McGill University, and he's going to give us a talk on his on the subject that's near and dear to his heart, fast radio bursts. Where are they and where are they coming from? Please make him feel welcome, Paul Schultz. Just give me the rundown. Forward, backward. Okay, and this is your laser pointer, I think. Whatever.
Is this do laser? Yeah, okay.
So we've got 45 minutes an hour, go for it.
Okay. Okay, so, well, thanks, Roman, for inviting me to give this talk. And this is an exciting topic, which is near and dear to my heart because it's a kind of a new field, and it's something that I've had the fortune to being involved in, at the very beginning when things are just starting out. So hopefully by the end of this talk, I'll let you know what fast radio bursts are and where they come from. So first, if I could say in one sentence what fast radio bursts are, I would say fast radio bursts are bright, millisecond-long bursts of radio waves that look like they're coming from outside the Milky Way. And this sentence will kind of serve as an outline for the first half of this presentation, and hopefully, I hope you will understand the implications of all of these, properties of fast radio bursts and what they mean by the end of the talk. So what a fast radio burst looks like in our data is, we're looking with our radio telescopes, we see nothing, and then we see a little blip that's about 5 milliseconds long. And so, first I will explain what I mean by radio waves. So, you probably know that light comes in a spectrum, and the visible light isn't all of the light that we see. There's shorter wavelength light, like X-rays and gamma rays, and there's longer wavelength light, like radio waves and microwaves. And so radio waves have wavelengths of about tens of centimeters to many meters, and in order to detect them, because their wavelengths are so long, to collect enough of them, we need to have big telescopes. And so this is a telescope that I tend to use. It's the largest radio telescope in the world, called Arecibo. It's in Puerto Rico, and it's about 300 meters across. So it's huge. And it was featured in the movie Contact, which I'm sure many of you have seen, being astronomy enthusiasts. And so, unfortunately, we don't actually sit at the telescope and listen to signals from space. That's just what they do in the movies. What we actually do is slap a computer or a bunch of electronics behind the telescope, record the data, and then analyze it, do all of our analysis later. So this is the instrument that we use for pulsar processing. I'll explain what pulsars are and what they have to do with fast radio bursts. Pulsars are my main field of interest before I got involved in fast radio bursts. Okay, so we have this huge telescope. What do we look at it with? So, what emits radio waves in space? Lots of things. I have a picture here of a radio galaxy. This is a massive galaxy that has this huge jet of radiation coming out of it. The structure is millions of light years across. And so you have this huge energetic outflow of radio radiation that's coming out from that galaxy. Also, supernovae emit radio waves. Here is a supernova remnant, so what's left over after a supernova, and the remnant is radiating in the radio, and it's shown in pink. So there are features that you can pick out in the radio that you can't see in the optical wavelengths using radio. And then also stars emit radio. Here's a picture of the sun in radio wavelengths. But the things that I care about are pulsars. So pulsars are rotating neutron stars that are about 20 kilometers across. And if you have something that's 20 kilometers across and it's across the galaxy from you, you can't make a pretty picture of it. So we resort to making an artist's impression animation. And what we actually detect in the radio is a little blip of radiation, like a fast radio burst, but I'll explain what's different between a fast radio burst and a pulsar later on. And so this neutron star is rotating. It can rotate it once per second, or even the fastest neutron star rotates 1,000 times per second. And every time the beam passes in front of points towards the Earth, we get a little blip of radiation. And so, as I said, they're 20 kilometers across about, and the mass of the sun, and spinning 1,000 times per second, which is about how fast your kitchen blender turns around. So these are pretty extreme objects. And where do they come from? So this will be relevant not just for pulsars, but for fast radio bursts as well. So pulsars, which are neutron stars, come from supernova. So when an H star dies, the nuclear burning stops, which is what holds it up from gravitational collapse, and it starts to implode. But then when the core of the star gets packed so tightly that it's as tight as the atoms can be packed together, it ends up bouncing back because it can't be any denser without collapsing into a black hole. But you need certain conditions to collapse into a black hole. And then you get the core rebounds because of that pressure, and the star explodes. So here's a nice little, artist's impression animation of a supernova. And then what's left over is a neutron star. If the core of the star is massive enough, the gravity is too strong and it will pull it into a black hole. But
Sorry, I have a question. How
Yeah.
accurate do you think that animation is of an actual supernova? How confident are you that?
I think it probably presents a good picture. We get an initial bright flash, and then we see something that fades but plateaus as the light curve plateaus as you have this expanding shell of material that's still radiating. So it's pretty, but of course we don't get this close to supernovae, so you don't see this much detail. But you can see these little structures in here that's forming in the expanding debris, and those structures are what we eventually see in supernova remnants, the structure we see like in that first plot I showed. Oops. Like, see, there's this structure in the supernova remnant. So this remnant will last many tens of thousands, 100,000 of years, and that structure there is what you see expanding out in this video. Okay, so I hope I've convinced you that lots of things emit radio waves, and that and explained what pulsars and neutron stars are. So now I'll explain what I mean when I say that fast radio bursts are a millisecond long, or about on timescales of a millisecond long. So nothing can travel faster than the speed of light. So if an event that's coming from space is a millisecond long, it means that whatever emitted it can't be smaller than the amount of time it takes light to travel from one side of the object to the other. And for a millisecond, the furthest light can travel is 300 kilometers. Now, the only things really in space, at least that could be emitting these high energy bursts that are that small, are neutron stars and black holes. The problem with black holes, of course, is kind of the definition of a black hole is that light cannot escape it. And so black holes can't really emit bursts. But you could imagine there are some models for fast radio bursts where you do have a black hole and you have something going on outside of it that could cause a fast radio burst. And I'll talk a bit more about that later. And this light time argument is the same argument that was originally used when pulsars were discovered to explain why pulsars had to be compact neutron stars. Now, you're probably wondering I mentioned these pulsars, which every rotation we get a little blip of radio radiation. And I mentioned fast radio bursts, which are little blips of radio waves. So, what's going on? Why don't we just call pulsars fast radio bursts or vice versa? Well, the reason is that fast radio bursts look like they're coming from outside our Milky Way. And pulsars, at least the ones we know of so far, if we take them and we put them far outside of our galaxy, we wouldn't be able to see them. They're just not bright enough. So these fast radio bursts are really bright. So now, what do I mean by that they're coming from outside the Milky Way galaxy? So, the term that we use in astronomy is that they're extragalactic. And so, the Milky Way is the galaxy that we live in, and the solar system that we live in is a very small portion of the Milky Way. The solar system is less than a light year across, and the Milky Way galaxy is about 100,000 light years across, and it contains billions and billions of stars. And here's a nice little artist's impression of it. Of course, we can't see the Milky Way galaxy from this angle because we live inside of it. So our nearest neighbor, the nearest major galaxy next to us, in comparable size to the Milky Way, is the Andromeda galaxy. And this here is actually real data from, I think it's the GALEC satellite, space telescope. And so the Andromeda galaxy is about 2 million light years away. So, about 20 Milky Way widths away is our nearest neighbor, Andromeda. But the universe, of course, contains way more galaxies than just two. So this is a picture of the Hubble, the Hubble Deep Field from the Hubble Space Telescope. I think it's the deepest image of the sky taken, except I think now they've moved on from ultra deep field to extreme deep field, maybe. I can't remember what the next step is called. But it is the deepest image of the sky, except maybe the extreme one. Anyways, this image contains about 10,000 galaxies in it. Pretty much every little point you see on it is a galaxy, even the little dots that you can barely resolve with your eye. And there's very few stars. These little things with patterns on them are probably stars, and the rest are all galaxies. This image is a very small portion of the sky. It's about the angular size of a grain of rice that you hold at arm's length. And so the sky is, just filled with trillions and trillions of galaxies. The universe is. I don't know if we can actually see trillions. Maybe if we build big enough telescopes, we will. But anyways, the fast radio bursts come from about a distance scale of 100 million to 10 billion light years away from the Milky Way. And so that is a good fraction of the size of the observable universe, and is definitely a lot further away than our local environment in the Milky Way, and even the local environment in nearby galaxies like Andromeda. And so, why do we think they're extragalactic? We don't actually have a little, ruler that we can take and put to the fast radio burst, and or a measuring tape long enough to put to the fast radio burst. What we actually do is we measure it from the properties of the radio wave, of the radio burst that arise at our telescope. So, just like optical light comes in different colors, when you put a prism, you shine it through, you shine light through a prism, it divides into colors. Radio waves come in different colors as well. So here is an image of the signal plotted with radio frequency, which is like color on one axis, and then time on the other. And what happens is that higher frequency radio waves arrive at our telescope earlier than lower frequency radio waves, and the degree of how much that delay is as a function of frequency tells us how far away it is. And the reason that it tells us how far away it is because this sweep as a function of frequency is caused by material between us and the source. So between us and a fast radio burst or a pulsar or any other radio source, any other source, I guess, there are charged particles. And these charged particles are what cause this sweep. And so we have models of how much charged particles are within our galaxy. We have models of how much charged particles there are spread throughout the universe between galaxies, and from that we infer how far away these fast radio bursts are coming from, and it looks like they're coming from a distance scale that's far outside of our galaxy. Okay, so I mentioned that they're bright, so how bright are they? So I decided to compare them to a few things. So of course, for me, I just compared them to pulsars because I'm familiar with pulsars. So that might not be all that meaningful to you, but it is 100 trillion times more energy output than a 1 megaton nuclear bomb. So, kind of scale of the largest explosion we could imagine making on Earth. An FRB emits the same amount of radio energy that the sun puts out in 300,000 years. So it's pretty, unimaginable scale. And importantly, to compare them to pulsars, to know that hey, these are something more extreme than pulsars, is that FRBs are about 10 quadrillion times brighter than your typical pulsar pulse. So I've explained, hopefully with some success, what fast radio bursts are. So now I'll give a little history lesson and a little bit of my role in it as well. So the first FRB was discovered in 2007 in science and astronomy. That's a very, recent discovery. The first burst was detected in 2007 at the Parkes Radio Telescope in Australia, and at first people didn't believe that it was real. It was a one-off event. It was way too bright for what you expect to see a source in the radio. So, a lot of people thought, okay, maybe it's just, a man-made signal that has been, just as a fluke masqueraded as an astrophysical source that makes it, that it looks like it's propagated through all this charged particles between us and the source. Or maybe it's some atmospheric phenomenon, like, lightning or something that is causing a signal that masquerades as an astrophysical pulse that has this signature sweep to it. But then with the same telescope in Australia, they discovered 4 more fast radio bursts, and they all looked like they were coming from space. They weren't consistent with coming from something close to the telescope, like man-made signals or atmospheric phenomena would. And so it was definitely getting a lot more convincing. And then in 2014, my colleagues and I discovered a fast radio burst at the Arecibo telescope in Puerto Rico. So now you have 2 telescopes, one in Puerto Rico, one in Australia, opposite sides of the Earth, and they're both detecting things. So that's a lot more convincing that these things. So at that point, we were pretty sure that they were a real astrophysical phenomenon, and that we have to explain them. So, before about a year ago, all fast radio bursts were one-off events. So people would see a burst, it would come from a position on the sky, and then they'd point their telescope at it and try to see if another one comes from the same place. And they never saw another burst from that location. So that made a lot of people theorize that, these things are so energetic that, they're pretty much the most energetic, they have to be coming from the most energetic things that we can think of in the universe. And a lot of these energetic events, like supernovae, destroy their source, right? In what we call in astronomy a cataclysmic event. So a star blowing up, a neutron star collapsing into a black hole, something where the source of the radiation is destroyed. And so naturally from that you would expect it to be one-off. But in 2014 we pointed, or not in 2014, the first burst was in 2014, but in the middle of last year we pointed our telescope, we being the P-alpha survey at Arecibo, where we search for pulsars and fast radio bursts using this telescope. So we pointed it at the location of the original burst, and we found more. So this is a huge step forward in the understanding of fast radio bursts. It tells you that the source of the radiation has to survive the initial event. And so this was a discovery that I was involved in. I was the one that got to have the eureka moment. So I'll give a little more detail into the timeline of things and the experience. So in mid-2015, like I said, we were observing the same location, and and then that data gets collected, and there's no Jodie Foster sitting here collecting our data for us. We record it onto hard drives. That data gets sent off to a supercomputer, one ran by McGill in Montreal. And on that supercomputer, we search that data for pulsars, for fast radio bursts. And so remember that prior to this, no other fast radio burst was thought to be repeating. So we thought, we're going to place limits on how often ours could repeat. We're going to provide evidence that this is also a one-off. But you should never assume something in science, before going in, because things can surprise you. So I was looking through the output of the data processing that happens on this supercomputer, and I saw this plot. Now, there's a lot of technical details on this plot, but I won't explain them, but the important thing is there is a nice bright burst here, and there are, and it was obvious right away. It's like, holy cow, this thing is repeating. This is a huge, discovery. And oops, sorry, I didn't mean to hit the mic. Immediately, all my office mates gathered around my computer, and I had to write an email to the collaboration. It was probably the longest email chain in my life, with lots of wows and good job. And it was very exciting. But that excitement, the excitement lasts, but what happened after this was we had to get down to work. We had to characterize these. We had to convince people that this isn't a pulsar in our galaxy, right? So there was a lot of work to happen and many months of work. And so those months of work went forward, and then eventually we published an article in Nature in this spring, in the science journal Nature, this spring in March 2016, and called Repeating Fast Radio Bursts, and it was led by my colleagues and I, and very exciting. And then immediately after this paper comes out, the press hears about it, and which is also very exciting to me. The first time in my life I get to interact with the press, and many articles were written. I did, 10 interviews or something, and then several other email interviews. But here I'll highlight a few of the headlines. I've picked out the National Geographic one because I actually really like that article. And I picked out the Washington Post one randomly. But I picked out this Universe Today one because it was one of the only ones that mentioned aliens in the title, and which I enjoyed. Nowhere in the article does it mention aliens. Nowhere. And so I hope by the end of this talk you'll understand the answer to this question: aliens or a rotating neutron star. We'll see. But anyways, the press behind this was, at least for me, a little bit overwhelming because, maybe that's because it's just my only experience. I don't know. So now, the second question that I posed in my title slide is, where are they coming from? And so two very important pieces of, when I say where are they coming from, I mean what's causing them. I mean, what's the physical mechanism that's emitting these bursts. And two important clues is that they're a millisecond long and that they are really far away. So that says they have to be coming from a compact region, like a neutron star or a black hole, and they have to be very energetic for that radiation to still be bright when it reaches us over such long distances. So basically, they have to be the most energetic things in the universe, basically things that go boom, things that make explosions. So supernovae, I show another supernova remnant here, which is what's left over after a supernova. Maybe I should have just showed the pretty video again, because that's more illustrative and, impressive. But supernovae are, stars exploding, very energetic events. But they're cataclysmic. They destroy their source, right? The star, if what you require for a fast radio burst is a supernova to go off, a supernova can only happen once. It destroys the star and you're left over with a neutron star or black hole, which can't have another supernova. But this would work for some fast radio bursts if in the next 5-10 years we find that there's one population of fast radio bursts that repeat and one population, or maybe more than one population, that doesn't repeat. A supernova could work to explain part of, to explain some fast radio bursts. Another of the most energetic things in the universe are gamma ray bursts. So gamma ray bursts sound a lot like fast radio bursts, GRBs versus FRBs. What gamma ray bursts are bursts from the other end of the electromagnetic spectrum in the gamma rays, but they're not quite as short as fast radio bursts. Thus, maybe the fast came from that. I didn't name them fast radio bursts, so I don't know where that came from. But anyways, a subset of gamma ray bursts are thought to come from merging neutron stars, so two neutron stars that merge together, and then they form a black hole. And what happens during that is a large beam of gamma ray radiation comes out and is very bright, especially if this beam is pointed straight at you, the observer. And so maybe there's also a way that you could make radio radiation during this event. And there are several theories that explain how nature might make radio bursts from this event. But again, this is cataclysmic. You merge these two neutron stars together, you turn it into a black hole. You can't merge those neutron stars together again. It's a one-off thing. But again, it could work if there's more than one explanation. Oops. So what are we left with for the repeater? So some of the most energetic explosions that happen in space that don't destroy their source happen on magnetars. So what magnetars are neutron stars. Sometimes they are pulsars. Sometimes we see pulses from them in, oops, did I press forward? I guess I did. Sometimes we see pulses from them. But they have very high magnetic fields. So these magnetic fields provide an extra energy source that can power activity or explosions on magnetars. So what can happen is you can have the magnetic field can crack the crust of the neutron star and cause something called a starquake, which emits a whole bunch of radiation, and you have a very bright event that can be seen quite a ways away. So the question is, could there be fast radio bursts, could there be radio bursts that come along with this event? And there are theories out there where they could maybe explain fast radio bursts. And this has the advantage that they're repeating. The explosions don't destroy the neutron star. And then for, maybe my favorite explanation, because I'm biased towards pulsars, but let's return to pulsars. So I said that pulsar pulses are 10 quadrillion times fainter than fast radio bursts, and so pulsars couldn't really work. And that's true for your normal garden variety pulsar. But we have one instance of a pulsar in our galaxy, and it's the Crab pulsar, which is in the Crab Nebula. You might be familiar with the Crab Nebula, but it also has this lovely pulsar wind nebula here, shown in X-ray data from Chandra and optical light from Hubble. And in the middle, you see a little neutron star. And so the Crab pulsar emits something called giant pulses, which are millions of times, about thousands to a million times brighter than normal pulses in the Crab pulsar. And it also has supergiant pulses, which are again another 1,000 or so times brighter than those giant pulses. And they're very rare, and they get emitted by the Crab pulsar very occasionally. But those supergiant pulses are still 100,000 times too faint. But the universe is a big place. There are there are millions of galaxies out there that these fast radio bursts could be coming from. If an event is rare in our galaxy, when you have millions of galaxies, it can be more commonplace. So say there are giant pulses that are many orders of magnitude brighter than those we see in the Crab that pulsars could emit. They're just, we don't see them in our galaxy because they're a very rare event. But if you have a volume of galaxies where you have many millions of them, this rare event becomes more commonplace. So what do we have for the future? So I presented to you a bunch of theories for where these could be coming from. So how can we differentiate between these theories? So one way is to figure out, are they all repeating? So we have to look at the existing fast radio bursts, look at the location of the sky they came from, and see if they repeat again, and if they're repeating similar to the Arecibo fast radio burst. And another way is to figure out, to pinpoint the galaxy that they're coming from. So, gamma ray bursts come from a certain type of galaxy. Supernovae occur in certain types of galaxies. Pulsars exist in certain kinds of galaxies. So if we are able to identify which galaxies the fast radio bursts are coming from, that will help. Unfortunately, when you point your radio telescope, you have your pixel size, your beam size on the sky contains many dozens to hundreds of galaxies in it. So you can't tell exactly where it's coming from, but we can use interferometry to get a better location. And then also just discovering a whole bunch more fast radio bursts would be great to build up statistics to see, are there multiple populations? Do we have a subset that are repeating and a subset that are not repeating? So to do that, to get lots of fast radio bursts, you need a sensitive radio telescope that can see a lot of the sky. And thankfully, we're building one of these in Canada. So in British Columbia, there is this telescope that is for, half pipes or cylindrical telescopes, and it has no moving parts. It just sits there and the sky moves over it. It is called the Canadian Hydrogen Intensity Mapping Experiment. So this was built originally to map hydrogen throughout the universe, but that's not what I want to use it for. I want to use it to find fast radio bursts. So what we're doing is slapping a gigantic computer behind it, which it's not shown in this picture, but sits right there in a little container, containers that ride on trains and ships and stuff. So a little, shipping container. And using that, we take a copy of the data. So the hydrogen intensity mapping experiment takes one copy of the data. We take another copy of the data and search it for fast radio bursts. And it's located in British Columbia at the Dominion Radio Astrophysical Observatory. And this is, exciting to me because I'll be starting a new job there in less than a month at the CHIME site, so that's exciting. And
is that an old site? Dominion Astrophysical?
Yeah, definitely. It's been there for quite a while. It's been a while since they've had a new instrumentation there, so CHIME is an exciting step forward. And so the power of CHIME is that it is these cylinders, and each cylinder sees a strip of the sky, a very large chunk of the sky, and using what we have is a bunch of electronics or receivers along the focal line here, and using powerful computers, which are also located over here, not in this image. Using powerful computers, you can use software to form distinct beams on the sky and pixelate this strip. And so you're able to map the sky very rapidly. Once per day, the sky passes over this strip, and so you get a map of the northern sky that you see from Penticton every day. And so it's a large amount of fast radio bursts. For comparison, the Arecibo telescope, 300 meters across a dish, can only see about a trillionth of the sky at once. So instead of having the whole sky pass above you once per day, you can only see a trillionth of the sky at one time with Arecibo. So it's a huge step forward in getting a large amount of sky surveyed in a reasonable time. So because of this large area of sky that we can see, the amount of FRBs that we're expecting to detect with CHIME is much more than we would expect that we've detected so far with the Parkes telescope in Australia and the Arecibo telescope in Puerto Rico. So the amount that the Parkes and Arecibo should see is about 100 to 1,000 bursts, or one burst per every 100 to 1,000 hours. And also with Arecibo and Parkes, we don't get to search for fast radio bursts and pulsars continuously with them. We only get to look for them when it's our assigned time to use it. Whereas at CHIME, we're going to have a dedicated instrument that sits right there and it's constantly searching the data that comes off the telescope for fast radio bursts. So we have basically 100% time on sky with CHIME rather than the 5-10% or whatever it is we can get with the Parkes and Arecibo. So it's going to be a huge boon in detecting a whole bunch of fast radio bursts and seeing, trying to deduce what they are. So thank you for listening, and I hope I managed to answer the questions what fast radio bursts are and where they might be coming from.
Thank you very much, Paul. Don't go anywhere just yet. I think it's questions. Yes, we'll have questions in just a minute. I'll just say that it's. So, if I understood your talk correctly, you basically discovered repeating FRBs.
Yeah. I had the fortune of being the one, who looked at the data at the right time.
Right place, right time.
Yeah.
That's impressive. No, that's really interesting. Actually, I'll just say an aside about Parkes, the Parkes Radio Observatory. If you want to see a really good movie that features the Parkes Radio Observatory, you can rent The Dish, which is a very good movie. It's about the moon landing, but it has to do with the tribulations that the Parkes radio telescope had to go through in order to get in order so that everyone who watched the moon landing could actually watch it. So does anyone have any questions for Paul? Oh wow, lots of questions here. We'll start down here.
Yeah.
Yes.
Is there a difference in signal you get from daytime or at nighttime? Like, is there more interference or like?
No, at the radio wavelengths that we observe these at, there's no difference. The atmosphere doesn't interfere. The radio waves pass happily through. The sun isn't a significant source of background, so we observe during the day and during the night, and so CHIME will be observing 24 hours a day.
What about weather conditions?
No, weather doesn't really affect radio at these wavelengths. So at shorter radio wavelengths, weather is a factor in radio astronomy, but where we're observing, it doesn't affect. The radio waves happily pass right through.
Gary?
Just a quick question. You're mentioning neutrons and pulsars. So a pulsar is pretty well a neutron star on steroids?
Pulsar is just a neutron star that has this beam of radiation coming out of it.
It's really fast.
Yeah.
That's why, because it has the beam.
Yeah.
Other than a regular neutron star that doesn't have a beam.
Yeah, so after a pulsar lives for about, 100,000 to maybe 1 million years, and after that it dies because it spins down to a point where, well, it doesn't die, it stops emitting radiation. pulsar astronomers say it dies because we stop seeing it. But yeah, it spins down to a point where it's not spinning fast enough to generate this beam of light.
Mike, at the back?
So I know gravity wave observing is really, really new, but would it be worth maybe correlating in the future gravity wave observations with FRBs to see if there's some sort of overlap?
Yeah, absolutely. If if the events that are causing the gravitational waves, which includes merging of neutron stars together, which is like what causes a gamma ray burst. So there are models for FRBs which do correspond to things that we would expect to see gravity waves from. Yeah.
Okay, I can see Brian at the back. You've got the microphone.
Yeah,
so
we've got a microphone available. We'll bring it around to people. Quick question: has any of these FRBs been discovered by more than one observatory at the same time?
No. So interestingly, we want to localize where the repeater is coming from, and so we're using a radio interferometer in New Mexico called the Very, Very Large Array, because astronomers are good at naming things.
Another Jodie Foster reference.
Yes, also in the movie Contact. So we're using that because you can take two telescopes that are spread apart. You can use that to triangulate the position where the radio burst is coming from, and you get a better localization of where it's coming from in the sky. So we are using that, and we are also at the same time as using that trying to observe it with Arecibo. So once we hope to make a detection of a burst that we see at Arecibo at the same time with the VLA, so that we can localize and figure out what galaxy the repeater is in. Yeah.
Where's the next? Is there someone close? Down here in the. Just wait for the microphone.
Just interested to know the scale of data that China is collecting, and are your search algorithms tuned so that you can find things before the incoming data overwrites them? And you must have problems with that.
Yeah, absolutely. The amount of data that's coming into CHIME is enormous. I should have a figure off in my head, but I don't. But many hundreds of terabytes a day, I'm sure. So you can't save that data.
Right.
So that's why we have to have a large computer, right there at the telescope, in a shipping container. I'm kind of amused by the fact that there's a large computer inside of a shipping container. But so you need that computing power right at the telescope so that you can search the data in real time, faster than the data is coming in. For fast radio bursts, we don't have the luxury of saving this data to disk, shipping it off to a supercomputer like we do with the Arecibo data. And so you only really get one chance to search for it, per fast radio burst.
Next question.
I saw one down here, and then I'll run them.
Yeah. We'll have a few more. And then we'll call it.
So you mentioned that you're hoping to use VLBI to be able to sort of triangulate where things are going. Are you using the Algonquin Radio Observatory at all in any of this work?
No, not yet. But we do have colleagues at the University of Toronto who work with that, and I think they're a little bit interested in it. So far, we've been using VLA in New Mexico, as well as something called the European VLBI network, which includes a whole bunch of telescopes in Europe, and as well as Arecibo hooked into that. So.
Next question back there.
I had a question about the beam coming out of this object. Is it coming out of the magnetic poles, or is it coming out some other way?
Yes, it's coming out. Well, it's thought that it's coming out from the magnetic poles. So where the magnetic field goes in, goes into the top of to the poles of the neutron star, the magnetic poles of the neutron star, there are a lot of particles hitting the surface of the neutron star there because the magnetic field is strong and it rips particles off the surface and then carries them to the other pole, depending on their charge. And then you get a whole bunch of charged plasma localized at the poles, which is what causes this beam of radiation.
The gentleman just behind?
Yeah. You said the first one was discovered in 2007, and the next one was in 2013. So why was there a 6-year wait between the two? Is there a particular reason?
Yeah, it is mostly that we were not expecting to see them. So I said that the first one was discovered in 2007. The telescope actually saw it in 2001. So it was observed in 2001 with the telescope. The telescope wrote the data to disk, and then eventually 6 years down the road, we got the computing power and to the point where we could actually search for bursts in this large data set efficiently. And then I say we, but this was before I was an astronomer, so they, the collective we, humanity, found it in those data much later. And then the 4 bursts, some of those were actually in 2001, and I think others were 2002, 2003, 2004. So these were old data that had been recorded in a pulsar survey and were searched for down the road when we had the computing power and I guess once we started prioritize searching for these bursts.
I think one last question, then we'll call it.
I'm just curious about why they kept the data from 2001 to 2007 when somebody could actually crunch the numbers. So I'm curious what was in that data that made them keep it. I mean, I'm sure you could have lots and lots of data.
Yeah. So the data was taken as part of a survey for pulsars, and we always know that in our data of pulsars that there are sources that are faint and really hard to detect, and we're constantly trying to improve our algorithms and make ourselves more sensitive to pulsars, and that includes more sensitive in old data. So as we get more computing power, we can do more clever things while we search for signals, and so that's why we keep the data around. We always want to keep data around so that we can process it later when people get smarter and well, not smarter, but we do more thinking, and the accumulated thinking over the years results in improved algorithms. Right? Yeah.
Okay, thank you very much, Paul. Thank you for coming out. If you want to speak to Paul, I'm sure he'll be available just after the meeting, and you'll also be coming down to Grace O'Malley's after the meeting. If for no other reason, then I'll be his ride back to his lodging. So Paul will still be around, so you can ask him any more questions then. Thank you very much once again for making the trip. Thank you very much for inviting me. It's wonderful to have someone to have the first discoverer of something, so to speak, presenting to us. All right, well, that brings us basically to the end of the most important part of the meeting. We'll just have the closing announcements. So as you saw earlier, there was we mentioned that the last star party that we had was very successful. Our next star party will be in August, at the end of August, and as always, the date will be up shortly. As always, it's held in the CARP Library parking lot, or Diefenbunker parking lot, basically. And there you are. So there's the Diefenbunker, there's the library, and there's the observing site. So just off CARP Road, you get off on the 417, and there's an exit, and you just head straight up. So we've had 3 primary dates in a row successful, and with the summer heat not abating, who knows, we might get number 4. The next one will be the 26th of August, or with rain dates of 27th August or 3 or 4 September. So keep those dates in mind. This is this is an event that's happening here at the museum. This is a book launch by Andrew Fazekas, or with Andrew Fazekas, the Night Sky guy, and the book is happening here, and it says it's happening at 2 to 5 p.m. on Thursday, August the 11th. Oh, sorry, I should say that's the book signing. And then from 8 to 8:45, you've got the actual book launch, and then stargazing from 9 to 9:30, weather permitting. So that's this Thursday, so in 6 days' time. That'll be happening here at the museum. If you can make it, please do. This is another announcement for the end of summer Star BQ. It'll be held at the FLO on Saturday, the 10th of September, or if it's a rain date, on the 24th of September. It starts at 5 p.m. and this is not open to the general public. It is open to members and their families. It's bring your own food, and the barbecues will be available for grilling, and you can. I'm sure it'll be a great time. Oh yes. Oh sorry. Yes, there is an. Oh yes. Sorry, I didn't see it behind the curtain, but there's an RSVP date. Please RSVP no later than the 31st of August to Martha_Farkas@Rogers.com, and there will also be updates on the website, on the Ottawa RAC website. Unfortunately, for the first time in a long time, the library is closed this month. Unfortunately, Estelle could not be here. Again, it's the Starfest, so there are a lot of our members are away at that. And now I'll show do my space weird but true. Does everybody recognize these fine gentlemen? Sorry?
Apollo 11.
Yes, that's. I believe that's Chuck O'Dale, isn't it? Yes, that's. Yeah, he never had very much, did he? Yes, this is the Apollo 11 crew, and if I'm not much mistaken, it's Aldrin, Armstrong, and Collins. Am I right?
Yeah.
Oh, okay,
You
good.
read the line.
I'm sorry?
You read the line on the screen.
Yes. Gary, you're just too funny. I don't know. All right. They were the first to land on the moon, though not the first to actually go there. I mean, there were Apollo 10 orbited the moon. They spent 8 days in space from the 16th of July to the 24th of July, 1969. Traveled about 800,000 kilometers. I suppose Michael Collins probably traveled the most of them, since he had to circle the moon a couple of times. And it was a dangerous journey. I mean, it was space. It's still pretty unknown. And I believe they suffered an oxygen leak on board, which was quickly patched up. It wasn't a serious emergency. The more serious emergency, obviously, was Apollo 13 later. But keep this in mind: dangerous journey. None of the three of them had any life insurance. They could not be insured. It was simply too risky. So, if they had died in space or on the way to the moon or on the moon, their families would have received nothing by way of payments. So, in order to alleviate any potential eventualities, the three astronauts signed photographs or postal covers of themselves in the event of their deaths, and these are called the Apollo postal covers. These would be sold to members of the public in the event that they died en route to the moon, or on the way back, or on the moon, and the proceeds would go to support their families. The estimated selling price, $30,000. And that wasn't just the asking price. That's if you wanted to buy some today as well. They still exist, and the originals, if you can get an original one, they're very expensive. And all the other Apollo missions made similar covers. So, practicalities of space travel. Can't get insurance, you might as well make some of your own.
And they did it all in their stocking fee.
Oh, did they? Oh, look at that. Stockings.
That's pajamas.
Those are pajamas. I actually read a statistic. What was the statistic? That every spacesuit costs a couple $1 million, but half of that cost is the backpack. So,
Roman,
yes?
another thing too, I hear that Neil Armstrong,
Yes?
he landed, he didn't like the landing where they're going to land.
Mhm.
He did it manually with 30 seconds left of fuel.
Yes, that's I had heard of that as well. That they just had to, I guess at some point you have to go for broke, and if you're going to go, I mean, they didn't actually spend all that much time on the surface of the moon, if I'm not mistaken. It was a 2-hour EVA. It was 4 days for a 2.5-hour EVA. But well, still, I mean, as they said, a giant leap for mankind. But I think they would have spent a bit longer. But no, it actually wasn't all that much time spent on the moon. All right, so these are the benefits of membership, and these are the costs of membership. $75 for regular membership, $70 for family, and $45 for youth membership. These are some of the membership benefits. You have access to the Ted Bean Telescope Loan Library, where you can take out a telescope for $10 for a month and then bring it back. You have access to the Stan Mott Library, where you can take out a book for a month and then bring it back. You also have access to the grounds of the Fred Lossing Observatory, but not to the actual sheds themselves, which require a separate fee, and you have to get a key for it.
And training.
Oh, is there training as well?
You have to be trained on the 16-inch to get a key.
Oh, okay, so there's training involved if you want to use the 16-inch telescope. These are some of the benefits of membership. You get these publications, and these are some of the officers or very important people who provide services within the club. Membership cards are available from Art Fraser if he has them, and if you haven't picked yours up yet. Our meetings are always streamed live at this URL, and older meetings are on YouTube. Also, if you go to Ustream, you can look at older meetings that have been uploaded. Usually they're uploaded within a very short time. So if you've just missed it, it doesn't take very long before the meetings are posted again. And this is part of our video archive.
The video archive is now complete.
Okay. So Eric has just told us that the video archive is complete, so that means it's all caught up to date. Thank you very much. I'm sure that took quite an effort.
About a year.
So today's audience, you can see, a bit smaller than usual, but good audience, 57 people.
Since I typed that, Gary says it grew to 68.
Oh,
I think his number.
68? All right, we'll go with 68. Like I said, I'm not good with measuring crowds, but there must be 20 million of you out there. So.
It's not quantity, it's quality.
Yeah, you keep telling yourself that, Gary. Thank you very much for coming out, though. Thank you very much. I know it's an effort. It's summer, it's hot, and it's cottage weather, and but thank you very much for taking the time to come out. Especially, thank you to Paul Schultz for coming down, and thank you to all of you for making the effort to make him feel welcome as well. So the post-meeting will be at Grace O'Malley's. If you go down the Aviation Parkway, turn right onto Ogilvy. It's, I think, one block. It's within 200 meters. So the next meeting, this is important, will not be on the first Friday of September. It'll be on the second Friday of September, and it's Friday, 7:30 p.m., September 9th, here at the Aviation Museum. And you can see we finally got a new background, a more contemporary background for the slide. Thank you very much. And so thank you very much, one and all, for coming out. If you want to grab another raffle ticket, we'll be drawing the door prizes shortly. We have quite a few prizes, and we also have one more special prize. I've brought a telescope for someone who wants it and who can win it at the raffle. So thank you very much for coming out. See you next month if I don't see you at Gracie's. Thanks. Thank you to all those who joined.